let's explore the extreme value of a quadratic function. Let's start with a quadratic function. We know that f has exactly one completed square form formula. And in this formula, the a is the same as in the standard form formula. The h is minus b over 2a, and the k is f of h. What about the graph of f? Two possibilities. First is that the graph opens upwards, and that happens when a is positive, and this vertex right here has coordinates h, comma, k. So f here has a minimum value, an absolute minimum value, that is. The value is k, and that occurs at x equals h. And over here, when the graph opens downwards, that happens when a is negative. And this vertex has coordinates h, comma, k. So in this case, when it opens downwards, f has a maximum value. That is an absolute maximum value. Let's do a concrete example. Let's look at this example. The quadratic function defined by the formula x squared minus 18x. First of all, what is the domain of f? Let's look at the formula that defines it. X squared minus 18x. That is defined for every real number x. So the domain is all real numbers, and in fact, that's true for every quadratic function. Right? Because every quadratic function is defined by a formula in the form ax squared plus bx plus c, and that is defined for every real number x. What about the graph of this function? What does it look like? Well, we have the standard form formula. And what we use to graph is the completed square form formula. So we need to figure out the numerical values for a, h, and k in this formula down here. A is the same a as in the standard form formula, which here is 1. H is always minus b over 2a. B in the standard form formula is minus 18 here. So h equals 9. And k is always f of h, which is f of 9. And to find a numerical value of f of 9, let's plug 9 into the formula for f that we have, the standard form formula. Minus 81. So f of x equals 1 times quantity x minus 9 squared plus minus 81. We simplify this formula, we get x minus 9 quantity squared minus 81. So the graph of the function defined by this formula. To do this, we start with the graph of the function defined by the formula x squared. This standard parabola right here like this. The vertex is 0, 0. And we see that in our formula, x minus 9 quantity squared minus 81, there's no reflection, there's no stretch, no compression. There are shifts, one vertical, one horizontal. So here we can do the shifts in either order. Let's start by doing the vertical shift. So let's look at the graph of the function defined by the formula x squared minus 81. I take the graph over there and I shift it down 81 units. The vertex here is that. And then do graph function defined by the formula right here. I take the graph above it and shift it to the right 9 units. And this parabola will open upwards. Let's see what the intercepts are. Right, this is the graph of y equals f of x. Let's plot the intercepts. Y-intercept of the graph of y equals f of x is 0, comma f of 0. Now, f of 0 is 0. Plug 0 into the formula for f, get out 0. And for x-intercepts, I set f of x equal to 0 and solve for x. Let's use this formula for f, x squared minus 18x. So the x-intercepts are 0, 0, and 18, 0. When we plot those, this gives a more accurate graph. Put this point over here. It's the point 18, 0. So f has a minimum value of minus 81 and that occurs at x equals positive 9. The range of f is, well, the minimum value is minus 81. And the graph rises unboundedly see that the range is minus 81, positive infinity, including that endpoint minus 81. The range is that.